All right, we're continuing our work in Unit 8. This is the last lesson, not Unit 8, sorry, Unit 7. This is the last lesson we have to do in Unit 7, and this is going to be applications of the dot and cross products. So the first application we're going to look at is work. And what's the definition of work? If you've taken physics, it's defined to be the product of the distance an object is displaced and the component of the force along the line of displacement. So if we think about that, here we have our vector f. This ON is the component of the vector along the force of along the line of displacement, right? So we're maybe moving an object along the line represented by OA, and the work would be, this is how far we've displaced it, so let's say the magnitude of OA, and then times the component of the force along the line of displacement, so we have to multiply that by ON. Now, of course, ON is going to be the magnitude of F times the cos of theta, so altogether we're going to get this formula here. So work is actually a dot product. I'm not sure if that's mentioned when you take physics, but work is actually a dot product. The magnitude of this force in the direction of S, which is the line of displacement, would be this times this. Again, as I mentioned, force is the force acting on the object. We're going to measure that in newtons. S is the displacement of the object. It must be measured in meters, of course, because newtons is kilogram meters per second squared. Work is done with the units. They're really Newton times meter or Newton meters, but work is referred to as joules. So we're going to call them joules. And theta is going to be the angle between the force and the direction of motion. If the force has a component in the same direction as the displacement of the object, the force is doing positive work. If the force has a component in a direction opposite to the displacement, then the force is doing negative work. I'm not sure if that's how it's presented in your physics class, but that's the way I'm going to choose to present it here. So calculate the work done if a wagon is pulled a distance of 200 meters by a force of 120 newtons at an angle of 25 degrees to the road. And again, because this is work, work is a dot product. So we'll start with that, work being a dot product. So it is the dot product of the force with the displacement vector. That's the magnitude of F times the magnitude of S times the cos of theta. Well, the magnitude of the force is 120 newtons. The displacement vector has a magnitude of 200, and the angle between the two is 25. So that is going to, so I've just switched it the other way around just so that you could see those two going together. It's not necessary to do that. So that's going to give us 200, and again, in physics you probably do it more like this. This is the displacement, and this is the component of the force in the direction of the displacement. So 120 times cos 25 is the component of the force in the direction of displacement. Altogether, we're going to go 200 times 120 times cos of 25, and then that is giving us, well, I think I have missed something there. Let me just correct that. All right, so continuing, I unfortunately didn't make that last calculation. I have to do 200 times 108.76, and just to show you, the 108.6 would actually be the component of the force vector in the direction of the vector of displacement. That actually ends up being 108.76 newtons in this direction, and then I times that by the displacement, which is 200. Altogether, that's giving me 21,751.39 or 0.4 joules. Again, Newton meters when we're doing work is expressed as joules. All right, let's look at our next example. So we are going to calculate the work if a desk is slid 5 meters across the floor against a frictional force of 100 newtons. And in this particular case, friction is opposite, or is acting in the opposite direction of the desk. So right now, if I'm pushing on it and the desk isn't moving, that means we're in equilibrium, and the force of friction is balanced by the force I'm exerting on the desk, but the force I'm exerting on the desk is in the opposite direction of friction. So again, this is work, and because it's work, we are going to be using the dot product formula. So work is the dot product of F and S, the force vector times the displacement vector. And we want the magnitude of F times the magnitude of S times cos of theta. And again, if I write it this way, then what I'm doing is I'm going to view it the way you would in physics, which is this is the component of the force in the direction of the movement. And this happens to be the distance that the object has moved. So the distance we're moving is 5 meters, and the frictional force is 100. But now the angle between these two is going to be 180 because they're moving in opposite directions. So let's show you that. I've got these technically in the wrong order based on what I've written there, so let's change that to 5 times 100. And then 100 times the cos of 180 would be the component of the force in the direction of movement. Now, because cosine is negative, cos of 180 is -1, I'm going to get 100 times 5 times -1, and that's going to be -500 joules. And of course, negative work being conducted here because they're in opposite directions. We had positive work done over here because this component was heading in the same direction. This vector was heading this way, which is in the same direction as the direction the wagon is moving. All right, so our next application that we're going to be looking at is areas. And so we can find areas using the magnitude of the cross product. Because it removes the directional component. Remember, the cross product is a vector, but the length of the vector is equal to the area spanned by the parallelograms. So I could find the area of this parallelogram by doing the magnitude of the cross product. And of course, the magnitude of the cross product is the magnitude of A times the magnitude of B times sine of theta. And if I wanted to find the area of a triangle then, spanned by two vectors, joining that up there, then it would be 1/2 the area of the parallelogram. So that would be 1/2 the magnitude of the cross product. That's going to give me 1/2 the magnitude of A times the magnitude of B times sine of theta. So our second example involves areas. Now, if we're going to find the area of a triangle spanned by these points, 1, 4, 5, B, -2, 1, 3, and C, -3, -4, 6. The first thing we have to think about, of course, is that these are not vectors, they are points. So you cannot take the cross product of points. It's a common mistake I see students making. We can't take the cross product of points. We're going to need two vectors, so we have options. We could find vector AB, we could find vector AC, we could find vector BC. So I'm going to work through some of those, and then we'll talk about how many we need in order to find the cross product. So the first thing I'm going to look at is a vector AB. So the sides of the triangle would be, well, instead of, I should make these vectors, right? Because if they're sides, then they wouldn't have a direction, and we wouldn't be able to write them as a vector. So we could have vector AB be one of the sides of the triangle. So in terms of finding vector AB, remember it's end minus start, so -2 minus 1, or alternately, I imagined translating this tail to the origin. So take away 1, take away 4, take away 5, and that is going to give me -3, -3, -2. I could also define vector BC to be another side in the triangle. And if we think about how that would work, we can plug into the formula, end minus start, or alternately, to translate this back to the origin, add 2, translate that back to the origin, subtract 1, to translate that back to the origin, subtract 3. So we'll get -3 plus 2, -4 minus 1, and +6 minus 3. And that is going to give us -1, -5, +3. And technically speaking, right now, we do have enough vectors to solve the problem, but let's just work on the last possible side for this triangle could be written as vector AC or CA. In this case, I chose to write it as CA. That means I need to translate the tail back to the origin. So what I would be doing is adding 3 to 1. I could be adding 4 to 4. And then I would be subtracting 6 from 5. And that's going to give me 1 plus 3 is 4. 4 plus 4 is 8, and 5 minus 6 is -1. So now I have my vectors. And once I have the vectors, I can definitely do a cross product. So choose any sides. It doesn't matter which side you choose, and you can verify after we've done this problem that if you choose a different pair of sides, you still indeed will get the same answer. So we could do AB cross BC, AB cross CA, or we could do BC cross CA. What I'm going to choose to do is I'm going to choose to do AB cross BC. So AB cross BC, again, I'm noting we can choose any two sides. I'm going to do AB cross AC, and maybe I'll just, write that out for you. So AB, we start with Y, we go to Z, to X, and back to Y. And then we're doing BC, so we're going to start with Y, we're going to go to Z, we're going to go to X, and then we're going to go back to Y, which would be -5. And let's just make sure we've got that correct now. -3 to -2 to -3, back to -3. -5 to 3 to -1, back to -5. So now we are going to be doing -9, take away +10. That's my X component. We're going to be doing +2 plus 9. -2 times -1 is +2. Take away -9. Now -3 times -5 is +15. Take away -3 times -1 is +3. So that's where those numbers have come from. And then when we're done, we're going to get this vector, the cross product vector being -19, 11, and 12. Now, in order to find area, what we're going to need to do is find the magnitude of this particular vector. Now, we can find the magnitude of this vector, so let me take you back over here. We wrote them this way. This definitely would be the area of the parallelogram, but because these are algebraic vectors we are working with, there's an alternate way to find the cross product. Once we've found the cross product, we can find the magnitude of that vector using the Pythagorean relationship. So the magnitude of this cross product now is going to be -19 all squared plus 11 squared plus 12 squared, and we need to take the square root of that. So the magnitude of AB cross BC, again, as I mentioned, from the Pythagorean relationship, the X component squared plus the Y component squared plus the Z component squared. If we punch all of this into our calculator, 19 squared plus 11 squared plus 12 squared, we'll get the square root of 626. And we should probably make sure that there's no perfect square factors of that. So 2 goes into 626, 313 times, 313 is prime, so we can't simplify it from here. Now, because we're trying to find the area of a triangle, this would be the area of the parallelogram, so to find the area of the triangle, we're going to have to take half of that. So half the magnitude of A cross B is going to be the square root of 626 divided by 2. That's our exact answer. And if we want to round, then we're going to round it to 12.51. And over here, I did write it down over there, but L9, in case you were wondering, what's hidden behind that button, that was the cross product. That's where these numbers have come from over there. All right, so that, I believe, is we started with work, we went to area. What's the next example we're going to look at? We can now look at the volume of a parallelepiped. Again, this would be so much easier if we were meeting face to face, because I have a 3D model of a parallelepiped. It's probably nothing you have seen before. But a parallelepiped is made by stacking parallelograms. So technically a rectangular prism is a parallelepiped because a rectangle is a parallelogram. But let's imagine a parallelogram that has really no special properties in that it's not a rhombus, it's not a square, and it's not a rectangle. So you'd get something that would look like that. Imagine stacking that to create a rectangular prism. Then what you would see is every face of this would also be a parallelogram. I need to find the volume of this. Now, how do you find the volume of a prism? Well, it's the area of the base times the height. So this is the base here. How are we going to find the area of the base? Well, that won't be problematic because I do know how to do that. To find the area of the base, I should find the magnitude of the cross product. So these two vectors, A and B, the magnitude of A cross B will give me the area of this, the base. So that's where this has come from. The area of the base is the magnitude of A cross B. Now again, if we were meeting face to face, what I would be doing is I would be coming around and I would also be showing you that A cross B creates a vector that is perpendicular to the base. So this vector perpendicular to the base, I can use this vector to find the height. Why? Because it's perpendicular to the base. So what I need to do then, here is vector C, where is the height? I need to project vector C back onto the cross product vector. When they meet at 90 degrees now, this pink vector, which is the component of C and the direction of A cross B, i.e. It is the scalar projection. It's a scalar projection of vector C onto A cross B. That's going to give me the height I need. Again, I'm going to walk through this again one more time. To find the height, I need to be coming perpendicular off here. Now what I prefer to do is to construct my perpendicular line right off the vertex where all three of these vectors are meeting. So right off the vertex of this parallelepiped. Now the vector that comes straight up is going to be perpendicular to the base. If it's perpendicular to the base, it is also the cross product. Then what I need to do is I need to project vector C onto A cross B so that they meet at 90 degrees, because then this pink bit here represents the height. And of course the pink bit is a scalar projection. It is the component of vector C heading in the direction of A cross B. So because it's a scalar projection, I'm just going to remind you, if we project A onto B, not this A and this B, but in general, if we project A onto B, it's A dot B divided by the magnitude of vector B. So what we're doing is we are projecting vector C onto A cross B. So then I'm going to need to take that, and I'm going to need to divide that by the magnitude of A cross B. So this little bit here that I've shown you now that's how you find the height. The height is created by projecting vector C back onto vector A cross B. And then what happens now are the A cross B's cancel out, and I'm just left with this little bit here, which we know as the triple scalar. So it's C dot A cross B. And then I'm going to have to put, this is not a magnitude surrounding it because this is a scalar. I'm putting an absolute value around it because it's possible that a scalar, not a scalar, a dot product, we know that the dot product can come back as negative depending upon the angle. And because this is the volume, we don't want volume to be negative, so we're going to put absolute value around that. So the derivation might have been a bit challenging, but the application of this formula is simple. We just take the cross product of any of the two vectors that represent the sides, and then we dot that with the third vector, take the absolute value of that. That's going to be the volume. And again, it bears repeating, so I'm just going to go through this sort of one more time. I'm just going to have to delete that whole thing. All right, so it bears repeating. So I need to find the area of the base. How do you find the area of the base? Well, the base is a parallelogram that's spanned by vectors A and B. If it's spanned by vectors A and B, then the magnitude of A cross B is the cross product, the magnitude of the cross product. The magnitude of A cross B returns the area of the parallelogram. We discussed that earlier. And then what I need to do is I need to find the height. Now A cross B is also this vector coming up. That vector is perpendicular to the base. The height would be perpendicular to the base. When you're finding the height of a prism, it needs to be perpendicular to the base. To get all the way to the top of this, I'm going to have to project from vector C back onto A cross B. They're meeting at a right angle. That pink length there is the height. And of course that pink bit there, based on what we did in lesson, I think what lesson that was, I think that was lesson 5 where we did scalar projections. So it's the component of C in the direction of A cross B. So therefore it's going to be C dot A cross B divided by the magnitude of A cross B. Those cancel out and I'm just left with that. All right, looking at our example then. So what we want to do now is we want to find the volume of the parallelepiped that is defined by the 3 vectors. Vector A, 0, 1, negative 3, vector B, 1, 2, 3, and vector C, negative 1, 0, 1. So remember the formula for the volume was we could do A dot B cross C. You have to take the cross product first, and then the dot. I had written it as C dot A cross B. It doesn't really matter which order we do this. Again, once I finish this example, why don't you try it in a different order, cross 2 different vectors? So the order in which I'm choosing to do it is I'm going to find A cross B, and then I'm going to dot that with C. So I'm going to drop the pencil so I can show you that. I'm going to start with A cross B, and remember, in order to find A cross B, how are we going to do that? We are going to start, whoops, put that back. We're going to start with the y component, which is 1, to the z component, negative 3, to the x component, that is 0, back to the y component, which is 1. Then moving on to vector B, the y component is 2, the z component is 3, the x component is 1, and the y component is 2. Always a good idea to check to make sure you did it right. We should be going 1, negative 3, 0, 1. We should be doing 2, 3, 1, 2. Now for the cross product, 1 times 3 minus negative 3 times positive 2. So we should be getting 3 plus 6. The next one, we're going to have negative 3 times 1, which is negative 3. 0 times 3 is 0, so we're going to get negative 3 minus 0. And in the next case, we're going to get 0 times 2 minus 1 times 1. That's going to be 0 minus 1. And let's drop the pencil so we can take a look at that. So again, 3 plus 6 is 9. Negative 3 plus 0 is negative 3. 0 minus 1 is negative 1. So that's our cross product vector. And then what we want to do is I want to dot this vector with the remaining vector, which is C. So I should have negative 1 times 9 plus 0 times negative 3 plus 1 times negative 1, which is exactly what we have here. And of course, I'm putting absolute value around that in case this comes back as negative. It is a volume, and volume should always be positive. So negative 1 times 9 is positive 9. 0 times negative 3 is 0. Positive 1 times 1 is negative 1. So that's going to give me the absolute value of negative 10. Of course, the absolute value of negative 10 is positive 10. So our third example was volume, and it was the volume of a parallelepiped. All right, that leaves us with one last application of dot and cross product. And what we're going to look at next is torque. And you may and or may not have taken physics, so I'm just going to quickly define what torque is. It's the tendency of a force to rotate an object about an axis. It's defined to be the cross product of the lever arm distance and the force. So imagine using a wrench, which I've tried to show you here. It's the cross product of the lever arm distance and the force. The torque is about point A, and it's created by the force F and the force acting on an object located. I'm not sure why I wrote that there. Point B should be point A. So torque itself is R cross F. Now, what I need to explain to you, though, is that in order to do this, the vectors are supposed to be coming on this particular side here, right? those vectors need to be coming together tail to tail. So although in the picture it would be drawn this way, I have to imagine sliding that there. So the angle we're talking about is actually this angle here. I'm not going to try to trick you. When I give you the angle, I'm giving you the correct angle. It would be this angle here. So if this angle is 20 degrees, then the angle that we're thinking of over here would be 160. But I'm not going to be attempting to trick you when I do this on the test. The angle I can give you, you can assume is theta. So torque itself is R cross F, and we would have to use the right-hand rule to determine our direction of travel. So if we were turning this in a clockwise manner, this way, then what would happen is the direction of the vector would be into the screen that you're watching now. If we turn in a counterclockwise manner, the direction of the vector would be coming out. To give you an idea, imagine if you're putting a screw or screwing a screw into a board. When you turn clockwise, it heads into the board. When you turn counterclockwise, it comes out of the board. We're not going to be worrying about torque itself. What we're going to be worrying about is the magnitude of the torque. So the magnitude of the torque will be the magnitude of R times the magnitude of F times the sine of theta. And again, R is the force acting on the object measured in newtons, and R is going to be the lever arm distance measured in meters. I'm going to have to underline this. It must be meters because it has to match. Newtons are kilogram meters per second squared. However, most wrench lengths are not going to be expressed in meters. They're going to be expressed in centimeters because a meter is very long. Now imagine a meter stick in a classroom. I mean, unless there'd be a very heavy-duty pipe wrench, but most wrenches are nowhere near a meter in length. It would make more sense to express the length in centimeters, so you're going to have to do a conversion. And that's, again, I've noted there why we have to be measuring in meters because of what newtons are. Torque is an overall twisting effect with units, Newton meters. Newton meters, when we're dealing with work, are called joules. But Newton meters, when you're dealing with torque, are just called Newton meters. Again, theta is the angle between the lever arm vector and the force vector when arranged tail to tail. And the direction of the vector, I noticed, is either clockwise or counterclockwise. We're either going to head into the piece of wood or out of the piece of wood. Now, that all sounds rather complicated, but the example problems we're going to do are straightforward. So a 15 Newton force is applied at the end of a 50 centimeter wrench. The force is applied at an angle of 75 degrees to the wrench. Calculate the magnitude of the torque about the other end of the wrench. And again, just, okay, here is my wrench, right here. And then we've got a force. I'm just going to draw a picture similar to what we are doing here. So I'm then going to have to translate this way. And then the force I'm applying on here so that this angle is 75 degrees. But I'm not going to ask you to provide a diagram when you do this on a particular test. We can just go straight into the formula. The magnitude of the torque, or the magnitude of the force that we are applying, would just be equal to the cross product, the magnitude of the cross product. That would be the magnitude of R times the magnitude of F times sine of theta. And remembering from over here that R is the lever arm distance in meters. And of course, that distance right now is expressed in centimeters, so I'm going to have to change that to 0.5 meters. And then my F vector force is going to be 15 newtons, and my angle is going to be 75 degrees. So I have 0.5 times 15 times sine of 75. Punching all that in, that gives us a force of the magnitude of the force of 7.24 Newton meters. And again, torque is expressed in Newton meters, not joules. So that brings us to the end of this particular lesson. Applications of the dot and cross product. I'm just going to quickly show you what they were again. We have torque. We have the volume of the parallelepiped. We have areas of parallelograms and triangles. And the very first example we did was work. If you've made it to the end of the lesson, thank you for watching. Always appreciate your support. Mr. Ciprietti always says I should tell you to smash that like button. So if you're so inclined, smash that like button and subscribe. Do stay tuned. There will be more videos on Unit 8. And as always, take care.